In this video, we are going to look at Bron-Kerbosch algorithm, which is a graph algorithm that calculates all the subgraphs within a given undirected graph. So we need to find all the maximal clicks that a particular undirected graph has. So what is a maximal click? It's a complete subgraph where every vertex is connected to every other vertex. And if we add another vertex to it, then the property of completeness of a particular subgraph is violated. If that happens, then we already have a maximal click. So a subgraph where a new vertices cannot be added. So if you look at the given graph, we can see and understand that 1 comma 2 comma 4 is going to be a maximal click, because if we add any other vertex, if we add 3 to this, then 4 is not connected to 3, so we don't have a maximal click, which is a complete subgraph. So 1 comma 2 comma 4 would be a maximal click. So this particular algorithm will find all such maximal clicks, and we are going to see how we can do this. So this is a recursion based algorithm, and for this we will be using three different sets, which is R, P and X. So R is the current click that we are going to calculate. So it would have 1 comma 2 as the 1 comma 2 or 1 as the current vertex, and we are going to make sure if this is the maximum click or not. That is what we have as one set. R. P would be the neighbors or the vertices, where if we add it to the current click, it will not violate the property, or we think it might not violate the property. And these are the potential vertices that can be added to the current click. Then in the end we have the X. This particular set is for avoiding duplicates, because if we have already processed a particular combination like 1 comma 2 comma 4, we have to make sure that we do not calculate 1 comma 4 comma 2 again, because that is already been that subgraph has already been analyzed, saying that this is a maximal click or not. So vertices that are already processed are kept inside X. So let's understand how this works now. We have three different sets, and to understand whether a particular subgraph is a maximal click or not, we just need to check whether the value of P and X inside any recursive call is empty. At any point, if this is empty, we know that we cannot add anything and everything is already processed and it is empty. So that particular subgraph, meaning that particular R with all the vertices, is the maximal click. That's how we are going to understand. Now, how do we calculate P and X? So P would be the vertices which are neighbors of the current R, right? Because we can't add all the neighbors of from a particular vertex, because the condition that the other vertex should also be connected to the vertices of this particular R, that condition should satisfy. So that is the reason we take the intersections. How we take the intersections is, whenever we need to calculate the new potential candidates or new P, we take the current candidates and we intersect with whatever the vertices are there inside the current R. We take all the neighbors of that, meaning we have, let's say we have 4 over here as P, and our R is like 1 comma 5. We have to make sure that the neighbors of 1 comma 5 are also part of the current 4. So we'll take only those vertices. It makes sense, right? Intuitively, if we take the intersection, we know everything in this is also connected to everything in the current P as well, right? And the way we calculate X is, we take whatever X we have right now, excluded vertices, and we just check the neighbors if they are already part of the intersection of all the neighbors of the newly added vertex, right? That's how we calculate the X whenever we go inside a new recursive call. All right, so now let's start understanding the steps. So I've done it for one vertex, that is for vertex 1, but the same process happens again and again, and you can just code that up and then you will be able to understand all the results. So we'll look at one such example. So the current state. So current state, we have R, which is nothing. So if the R is empty, all the candidates of the graph, all the vertices of this particular graph are the potential vertices that can be added to R to create a maximal click, and the X is initially empty, right? The first recursive call, we add 1, we choose the vertex 1, right? Now we need to understand what are the vertices which are neighbors of 1 and also present in this. Okay, so we take the intersection of that. So current P, this is a current P, intersection with all the vertices, all the vertices in the current R. In the current R we have 1. So the neighbors of 1 are 4 and 2, right? So we do an intersection of 1 comma with all the current P with 2 comma 4. So the intersection is 2 comma 4. That's how we know that we shouldn't check 5 because it is not connected to 1 or any of the other elements that we add to R now. Okay, for at least at this particular stage at the recursive call. Now we calculate the x. So initially it was empty, so current intersection of whatever we added right now, so we added 1, the neighbors of that, so that's 2 comma 4. Again it is empty, so x is empty. Now do we know whether this is the maximal click or not? We just have to check whether P is empty or X is empty. So X is empty but P is not. P has some vertices, so we need to handle that too. Now we go inside the recursive call. So this was step 1. Now we go inside the recursive call for step 1.1. We choose 2 from this. Okay, when we choose 2, our new R becomes 1 comma 2, and now we need to find the vertices where all the neighbors of 1 and the current P are together or connected to each other. This can be found by taking the intersection again. So 2 comma 4, then the neighbors of 1, that is again 2 comma 4, and then all the neighbors of 2. So the neighbors of 2 are 1, 3, 4 and 5. So that's what we have taken here. So intersection of all these 3 would be 4, correct? And then again we try to find the x, whether we have anything or not. So empty intersection, the neighbors of whatever we added right now. So we added 2, so it would be empty again. Now is 1 comma 2 the maximal click? No, because we have 4 still and this is empty, so this is not yet empty. Now we need to handle 4 as well. Now this is a new recursive call. A new recursive call goes into 1.1.1. okay, now we have chosen 4. Now we have to understand the current neighbors of all 4 are part of this particular 4 also or not. So 4 intersection, so neighbors of 1, that was this, neighbors of 2 was this, so the answer was 4, which, okay, and then the new neighbors of the newly added vertex. So 4 intersection 1 comma 2 comma 5. So when we go to 4, neighbors of 4 will be 1 comma 2 comma 4. So these are the 1 comma 2 comma 5 are the neighbors of 4. Now here is where we get an empty P. Nothing is common, meaning that none of the neighbors can be added now, where everything also is connected to the new vertex. So 1 comma 2 comma 4 gives P empty, and here also we have X as empty. Now we can say the maximal click has been found, and that is 1 comma 2 comma 4. Now this has ended the recursion at this particular level. So we go at the previous recursion, which is 1 comma 1. At this location we had already used 2 and have checked for each and every neighbors of 2. Okay, so now 2 goes inside X, so we should not include 2 again when we start processing the previous recursive call, which is a 4, right? So now 2 is added to X. So our new state would be, now we go to a next recursive call where 2 has been added to X and 4 has been chosen as the next recursive call from the initial 2 comma 4 recursion that we started at step 1. So that's the first recursion call. We have added 1 comma 4, right? So 4 is here. Now we need to check the neighbors of 1 and 4. So neighbors of 1 is 2, neighbors of 4 is 1 comma 2 comma 5. Here also we got P as empty, right? But in this case X is not the X is not empty, meaning the combination 1 comma 4 comma 2 will not be calculated because X is not empty, because we have already found that combination before at step 1 comma 1 comma 1, right? In this case we just return back to a previous recursive call, which goes to this particular recursion, the first recursion that we started. And we can conclude that since x is not empty, p is empty, we cannot find a maximal click, and that's it. The recursion ends. So one recursion gets completed with vertex 1. Now this was the first recursion that was started, and we add this one to the x, right? Now when we go to the next vertex, which was step 1, where we started with all the potential candidates, we remove 1. Now we add 2, and this particular one would be added to x, which is written over here, right? This is how you start the new recursion. So now we have an empty R, we have all the potential candidates, and since we have already processed 1, it is here. Now we start again. So 2 is chosen, we take this particular p, and then the neighbors of 2, and the common would be 3, 4, 5. We come here, we have 1 here already, 1, 3, 5, we have 1 here, correct? And this would be the inside recursion call. So this is how you keep on recursing, and at the end you would find maximal clicks like this, wherever p is empty and x is empty. Once you do this, the final result would be 1, 2, 4 from vertex 1, and from this particular recursion of vertex 2 we get two clicks, 2, 3, 5 and 2, 4, 5. In the end, when we go to vertex 5, now we know that only 6 is the neighbor which is also connected to each other. So this would be another maximal click that we can conclude. So these are the 4 different subgraphs which are complete, can be found using recursion, and each of them can be calculated by intelligently choosing which potential candidates have to be considered to be added to the current graph or the current vertices that we are choosing. So that's how Bron-Kerbosch algorithm works. This is what I wanted to show you in this video. Hope you like it. Thank you.